All right, so we are going to look at one more kind of physical application, and that is centers of mass. So we're going to start off with centers of mass of a in a one-dimensional context. And kind of the best way to think about this is the idea that we've got in our picture down below here, two masses that we're trying to balance on a teeter-totter. So we've got maybe, for example, one is heavier, one is lighter. And so where would we position this, the fulcrum, that is the sort of the what we balance on, where would we place that so that our teeter-totter would be balanced? So how we're going to do that is we're going to look at the position of where each of the weights are, how much they weigh. So we want to find the center of mass given some masses and positions. So kind of what we can think about here is that we've got a number line starting at 2, there's 3, there's 4, ending at 5, and we've got a mass sitting here at 2 of 40 grams or pounds. It doesn't, the units don't really matter. Show you why here in a second. And then we've got a mass sitting at 5 of 30. So the idea is, where are we going to put that fulcrum? Where are we going to put that balancing point so that if we had this on, say, like a teeter-totter, it would balance out. So what we're going to do is take basically the average of our masses and where they're sitting. So we're going to go 2 times 40, so that's our position, and then our mass, plus 5 times 30. Again, our position times our mass. And then we're going to divide that by the total mass that we have. So total mass. And if you think in terms of units that we've got here, we're going to get sort of like position mass on the top. Maybe we'll write that down here, that like units wise, say if it was inches and pounds or foot, maybe we'll do feet and pounds. We would get foot pounds on the top because we get feet times pounds. And then on the bottom, we'd have pounds, and then this would cancel out and give us feet. So that would give us a location. So it doesn't really matter if it's in kilograms or meters or what it is. We're going to get whatever our unit is. So again, back to our calculation. We're going to get 80 plus 150 divided by 70. So we'll get 230 over 70, or 23 sevenths. And I'm going to get the approximation for this because I don't know exactly where that point is on our number line. So 2.3857 is where we would put the fulcrum here. And so that's going to be kind of about right there, maybe. Maybe we'll draw that a little bigger. We'd put it right there to balance it out. So it's got to be a little closer to our heavier weight versus our lighter weight. So if we had more weights positioned, on different spots on the number line, we would just add more of them up. So this leads us to a theorem that's from our textbook, that we've got the total mass here. It's all of our masses added up. And then what's called the moment. So up here we have the total mass, the top of this fraction. It's called the moment. And that is all of our positions times each of their masses. So we've got a summation there. And then the center of mass is that moment divided by that total mass. And so what doesn't change, if we think about this a little more two-dimensionally, is that to figure out our total mass, we still do the same thing. So we're going to look at this now in 2 dimensions. And basically the idea is that we're going to have several masses, usually 3 or 4, in the XY plane. So they're going to be sort of placed around in the XY plane. And you could think that, we're making sort of a triangle or a rectangular type solid, not solid, but like plate, sort of whatever they're sitting on with each of these masses at the corners. And the idea is, how would we balance this with these different weights? So our total mass is the same as before. It's all of our masses added up, so however many masses that we have. And then we've got our two different moments. We've got m sub x and m sub y. And the notations are a little bit misleading. At least I always have to think about this, so I have a little note down here for them. So notice m sub x, it is our moment where we multiply all the masses by the y position. So m sub x is really how far the masses are from the x-axis. And so this is going to have us look at our actual y values, because the y values give us how far away we are from the x-axis. And then m sub y, this is how far the masses are from the y-axis. And this is going to have us looking at the x values. Oops. Because the x values are how far away we literally are from that y-axis. So we could draw a little picture down here of a point, say, sitting out here, x sub I, or x sub I and y sub I, and how far we are from the x-axis. That is y sub I. That's our distance from the x-axis. Similarly, if we looked at how far we were from the y-axis, that's x sub I. So that's why it's noted the way that it is, so that when you go to find your center of mass, the sort of average of the x values is that m sub y, so how far all those points are away from the y-axis, so the x values actually averaged up with over the total mass, and same with our center of mass. The y coordinate, it's that m sub x, but again, it's how far all of those values are from the x-axis. And that notation with that bar over the top, that does mean average. So we're kind of like averaging out the positions and the weights. So let's take a look at an example of this. So find the center of mass given the masses and positions. So mass 1 is 6, again, a weight of 6. We don't need a unit for this, but we could draw where this is sitting. So 1, 2, 3, 4, 5, I guess that would be sitting up there. So that's where our mass 1 is going to be at 1, 5. Our mass 2 is going to be at 3, negative 2, so that's where mass 2 is sitting. And then mass 3 is at negative 2, negative 1, so there's mass 3. And so we can, like I was saying, we can kind of view this like we've made like a plate of some sort, where each of these is kind of sitting out on a corner, and we're trying to figure out, where would we need to sort of position this on a pole so like everything would balance perfectly. So the things that I figure out are the total mass, and that is that lowercase m. So that's just all three of our masses added up, and we get 21. And then that m sub x, that's that sum of our masses times our y values. So again, it's a little annoying that it's kind of opposite of what it seems like it should be, times negative 2 and then 10 times negative 1. So again, what I'm doing is taking each of my masses and each of my y values. So we've got mass sub 1, y value sub 1, mass sub 2, y value sub 2, mass sub 3, y value sub 3. We do a similar thing for that m sub x. This is going to be the sum of our masses times our x values. So this is going to be 6 times 1 plus 5 times 3 plus 10 times negative 2. I guess I should actually do these calculations because we need these numbers. We get 10 here for the m sub x, and we get 1 here for the m sub y. So our center of mass, where that's going to be, it's going to be, remember, it's m sub y for x over our total mass, so 1 over 21, and y is m sub x over m. So again, we're just getting that from our formula here. And if you want to see where these formulas come from, you can see that in OpenStax. So what this gives us is the point on the coordinate plane where we have that balance point. And so I'm going to figure out what this is as a couple of decimals so that I can kind of, take a look at it on the coordinate plane and make sure that it seems to make sense about where it is. And so it's not too far from the origin. So the x value is 0.04, so really close to the origin, and then up a little bit more than a half. So that's our center of mass. And that feels like that makes sense. It's sort of closest to the heaviest mass of 10, and it's almost kind of in the middle of that 5 and the 6. So kind of makes sense of where that's sitting.